This is the second part of the lecture on sequences, section 11.1. We start with two definitions, and these definitions are ones really that you have already had concerning functions. When functions are bounded above or bounded below, well, the definition for bounded sequences is really just the same. A sequence is bounded above if every term of the sequence is smaller than some number a, and a sequence is bounded below if every term of the sequence is bigger than some number b. Some examples are, the first example here, a sub n is equal to cosine n over n. And we would like to find an upper and a lower bound, or say that the sequence is unbounded. Well, let's see, here we know that cosine n is always less than or equal to 1, greater than or equal to minus 1. And since n is positive, a positive integer, we can divide through by n, and the inequality signs keep the same direction. Now 1 over n is always less than 1, and minus 1 over n is always greater than minus 1. So we have found a upper and lower bound. Negative 1 is a lower bound, and 1 is an upper bound for this sequence. Now, there are infinitely many lower bounds. I could also say that negative 10 is a lower bound, or pi is an upper bound. And b sub n, well, we could rewrite that. We only have one term in the denominator, so it probably would be helpful to write this as 2n over n, which is 2 minus 1 over n. And then we can see better the bound, can't we? We know that 1 over n goes to 0 as n goes to infinity, so this b sub n is never equal to 2. It's always less than 2. So I could say b sub n is less than 2. 2 is an upper bound. And also 1 over n being less than 1 will always make b sub n greater than 2 minus 1, which is 1. So again, we have a bounded sequence, bounded below, bounded above. A sequence is called monotone if it is increasing. In other words, the terms just get bigger and bigger, or decreasing if the terms become smaller after some point in the sequence, after some index. Now, if a sequence is, well, let's look at the examples that we looked at before. We had one example, braces 1 over n, on the previous slide. We know that 1 over n is 1, 1/2, 1/3, etc. So we know that it is a strictly decreasing. It is strictly decreasing. From n equals 1 on, we can say that a sub n plus 1 is less than a sub n. So we have a decreasing sequence, monotone decreasing. Now the other one we looked at was the sequence, what was it? 2 minus 1 over n. 2 minus 1 over n on that last slide. And this one we saw, well, as you subtract smaller and smaller and smaller amounts, we see this sequence is increasing. In other words, a sub n plus 1 is bigger than a sub n. Or I could write 2 minus 1 over n plus 1 is bigger than 2 minus 1 over n. So we have a monotone increasing sequence, and 1 over n was a monotone sequence, monotone decreasing. But something the author doesn't mention, that is also important is that the behavior of a sequence is not really determined by what happens in the first 50 terms or the first 100 terms. It's what happens, the tail end behavior of a sequence. So for an example, I just wanted you to see one. We know that powers of n will beat out powers of natural log n eventually. We know that this sequence, in fact, will eventually get close to 0, and that its limit is 0. But look at the graph of this sequence at the beginning. I've plotted the first 100 terms here. It sure doesn't look like it is decreasing. In fact, at the front end of the sequence, the first 100 terms, this is an increasing sequence. And on this slide, I continue to plot points, plot the sequence. A sub n is equal to natural log to the 5th divided by n. And you see that the high point here is after about, I think it was n equals 148, 149, we see that the sequence does start to decrease. And in fact, the graph, if I was to plot the first many terms, it looks like this. But it doesn't get close to 0 until well, it doesn't even get less than 1 until n is equal to about 330,000. So it's way out there. It's way out there that the sequence gets close to 0, that the terms of the sequence do. And although this is not a monotone decreasing sequence, we could say that it is eventually decreasing. I could, in fact, say let n be equal to 150, a little bit after 148. Let n be equal to 150, then n, if we choose little n, our index bigger than capital N, that will give us a sub n is bigger than a sub n plus 1. After n equals 150, the sequence becomes decreasing. We could say it is eventually monotonic decreasing. The theorems that we will have regarding monotonic sequences will not just apply to sequences that are monotone from n equals 1. They will also apply to any sequences which are eventually monotonic. So we would like to see what is special about monotonic sequences, or eventually monotonic. Let's look at the first one here, the first example. We have a sub n is the cube root of n. So the cube root of n, let's just write out a few terms. When n is 1, we have the cube root of 1, and then the cube root of 2, and the cube root of 3, and so on. And we know that n to the 1/3 will just increase. And its limit, in fact, we could put arrow infinity. It does not converge, but it is increasing. These are all increasing sequences. So it is a monotonic increasing sequence, and it diverges. And the only way it could diverge, the only way it could not have a limit, is to become arbitrarily large without bound. The next one, we have n over n plus 1. So let's write out a few terms. We have 1/2, and then we have 2/3, and then we have 3/4. And well, n over n plus 1 never gets bigger than 1. But look, it continues to increase. 4/5, 5/6, and we know that it does converge. The limit is 1. But it is an increasing monotonic sequence, and it either will have to diverge or it will have to converge. Notice that this sequence is bounded. N over n plus 1 is less than 1, or we could say less than 10. But it is bounded above, and it is increasing, and it converges to 1. Another example, arctan n, okay? Arctan n. Write out a few terms. Well, we don't need to write them out because we don't know their exact values. Let's look at a little picture. We know that arctangent has a horizontal asymptote at y equals pi over 2, and the terms of the sequence are just the points of the graph that have integer x-coordinates. And I don't know how to evaluate those in my head, so I'll just draw a picture. We see that arctangent is a monotonic increasing sequence, and it is bounded above by pi over 2. Well, if it's bounded above by pi over 2 and yet it is always increasing, then it must converge, because a sequence that is increasing that doesn't converge has to get large, that is not bounded above, has to get large without bound. It has to go to plus infinity. So this will converge, and in fact we know it converges to pi over 2, its least upper bound. Now let's look at some decreasing sequences and see if we could conclude something about when do decreasing or monotonic decreasing sequences converge. Well, the first one, we see 1 over n minus n. Well, let's see, we have 1 over 1, first term is 0, and then we have 1/2 minus 2 is minus 3/2, and then we're going to have 1/3 minus 3 would be minus 8/3, and then 1/4 minus 4, or 1/4 minus 16/4, we have minus 15/4, and we see that it's just getting smaller and smaller without bound, and so it will just diverge, becoming more and more negative. So if a sequence is decreasing without bound, then it simply is not going to converge, and it will in fact have well, not a limit, but it will go to negative infinity. Now what if here's 1 over n. This is a decreasing sequence. We have 1, 1/2, 1/3, etc. We know that 1 over n is a decreasing, monotonic decreasing sequence, but it is bounded below. It does not decrease without bound. It is bounded below by, in fact, the number 0, or -1, or minus 100, but 0 is its greatest lower bound, and in fact we know that the limit of 1 over n as n goes to infinity is equal to 0. One more that is bounded, let's look at the nth root of n. The nth root of n. We know this is n to the 1 over n, and I proved in a previous video that the limit is 1. But let's look. We have 1, then we have the square root of 2, the cube root of 3, the fourth root of 4, and this sequence starts decreasing after the first term. Of course, the square root of 2 is bigger than 1, but from here on, these numbers continue to decrease towards 1. Notice if this is a decreasing sequence, it is bounded below. We can say that a sub n is greater than or equal to 1 for all n. Therefore, it is bounded below, and it does converge, in fact, to 1. So if a sub n is a decreasing sequence, then it is either bounded below or it's not, and it either converges or not. If it doesn't converge, then you know, since it is decreasing always, it must go to negative infinity. That's the only way that it could diverge. If it converges, it will be bounded below. Let's look at one more example. How about the sequence 1 minus n cubed over n squared? This is a sequence, and let's see what's happening to it. Let's write out, well, you could write out a few terms, but I'm going to just take the limit. I'm going to divide the numerator and denominator by the most powerful term in the expression, which would be n cubed. N cubed is what's growing the fastest, so I divide by n cubed each term. N cubed over n cubed is 1, and n squared over n cubed is 1 over n. Now I look here and I see 1 over n cubed goes to 0, 1 over n goes to 0. So the numerator of this goes to a constant, negative 1, and the denominator is going to 0. And we said that means it diverges. And in this case, we see it will diverge to negative infinity. The bottom is going to 0 through positive values, and the top is going to negative 1, which is, of course, negative. So it would again diverge to negative infinity. We see another example of a monotonic decreasing sequence that is not bounded below. It must diverge to negative infinity. This is a very important theorem that we will use in our study of series. An increasing sequence that is bounded above will always converge, as we saw 2 slides ago with our examples. And a decreasing sequence that is bounded below always converges. You could see that because if it's always decreasing and it's bounded below, it has to converge. Now, we're not proving this. You'll prove this in a later course, but this is extremely important and pretty obvious, really, when you look at the examples that we looked at. Every bounded monotonic sequence converges. And really, they don't have to be monotonic from n equals 1. As we saw in our example, natural log n to the 5th power over n was not immediately decreasing, but after n equals 150 it was, and so it was eventually monotonic decreasing, and it was bounded below by 0. So we knew that according to this theorem it will converge, and we know that it does. It converges to 0. As long as a sequence eventually is increasing or decreasing, or eventually monotonic and bounded, it's going to converge. It would be nice if we could say that all sequences that converge are bounded and monotonic, but, well, they would be bounded, but they certainly would not have to be monotonic. For example, look at these examples. The first one, minus 1 to the n over n. Well, we'd have minus 1 over 1, and then we would have minus 1 squared, which is 1/2, Then we'd have minus 1 cubed, which would give us negative 1/3, and so forth. So you see, this definitely converges to 0, but it is not monotonic. Same thing, of course, with sine n over n. We know we have proved using the squeeze theorem that this converges to 0. But sine n is negative sometimes, positive sometimes, and so this is not a monotonic sequence ever. But they do converge. So the answer is yes. A sequence does not have to be monotonic to converge.